This lecture introduces our laboratory experiment involving torque. Our purpose here is to measure the rotational inertia of a pulley. Measure the rotational inertia. Pulley. Okay, there's going to be some theory behind the experiment. As always, make sure that you describe the theory in the first section of your laboratory report. Okay, here's going to be our laboratory setup. Okay, first of all, we're going to have the desk like so, and then I'm going to clamp a ring stand to the desk like this. And then clamped to the ring stand is a pulley assembly, like so, such that the end of the pulley here, or the edge of the pulley, is draped out over the edge of the desk. And then what I'm going to do is I'm going to take a mass M, tie a length of string to it, and then tie that around the pulley like so. So let's say that right here, for example, is our mass M. The mass M, by the way, is equal to 0.2 kilograms. Okay, and then I'm going to release the system from rest such that the acceleration occurs in this manner. So let's set up F equals ma, first of all, for the little mass that's attached to the string, and then we'll set up tau equals I times alpha for the pulley itself. Okay, first of all, the force is acting on the mass. Okay, so acting upon the mass, we just have two forces. We have the tension from the string and mg downwards, like so, and then therefore the acceleration is downwards, such that when we add up the forces, we get mg minus t is equal to ma. Okay, and then let's go ahead and take a look at the torques that are exerted upon the pulley. We're going to treat the axle as frictionless, and the string does not slip on the pulley. Therefore, we're only going to have one torque vector, and that's going to be due to the tension force that's applied tangential to the pulley. Okay, so right here, for example, let me draw it off to the side, like so, is the tension T, and then right here is our moment arm, capital R. So off to the side, right here is capital R, and right here is the tension. They're perpendicular to each other. So now when we calculate the torque, it's going to be R cross F into the board, and this is going to be a positive torque because ultimately the fingers in my right hand here are curling in the same direction as the tangential acceleration, which is the same as the acceleration A. So then therefore I'm going to have the positive torque, and that's then going to equal I times alpha. Now because the string does not slip on the pulley, the angular acceleration alpha is equal to the acceleration A, and then divided by the radius capital R. So let's go ahead and plug that into here. So I get R times T equals I times alpha, which is A over R, like so. Okay, now in the procedure, I'm actually going to take us through the process of how we measure the acceleration A and how we measure R, the radius of the pulley, but what we're not going to measure is the tension. So let's go ahead and algebraically just combine the equations together and then solve for the rotational inertia I. Okay, so I'm going to solve for T here, so move the R down to the other side of the expression like so. And then take this expression for the tension, and then we'll plug it into here. Okay, so mg minus the tension, so minus IA over R squared is equal to ma. And now what we do is we algebraically solve for I. So I'm going to take these two terms here and just switch them. So, and then just cross multiply the R squared and the A over to the other side to solve for I. So in doing so, I then end up with the following. This rather weird looking expression here, like so, as the rotational inertia I. So we already know what the mass M is. That's given as 0.2 kilograms. And then in just a few moments when I take you through the procedure, I'm going to lead us through the process of measuring A and also measuring R, the radius of the pulley. Okay, once we have those measurements, then we plug everything into the expression, and then we just measure the rotational inertia I. At the end of my description of the experiment, I'll give you an understanding as to what you should calculate for the value of I, but there's going to be no theoretical value. We're not going to calculate a percent error when it comes to error analysis. Okay, now let me take you through the procedure. Okay, so the procedure is to set up the situation as I've described. What I then do is I take a piece of strip tape and I tape it to the mass M, and then I thread the strip tape through the spark timer. So here's basically the same diagram. Once again, here's the edge of the desk like so. The ring stand is clamped to the desk. Okay, right here is the pulley assembly like this. Right here is the mass M. And then what I do is I attach a piece of strip tape to the mass M like so, and then thread it through the spark timer, which is up here like this. And then basically all that I do is I turn on the timer and then just drop the object. Turn on the timer. And then actually what I do is I dangle the object here such that the string is taut the whole time, and then I just let go of the pulley. Okay, at this point, pause this lecture and go ahead and take a look at the video that I've posted for you that shows me doing this setup and obtaining the data that we'll need, obtaining the strip tape that we'll need to ultimately analyze the experiment. So take a look at that video now. Okay, the strip tape that I obtained from that video is going to be just fine for our purposes here. So then therefore, let me take you now through the analysis. Okay, so we've analyzed spark tapes before in previous experiments. Our analysis here is done exactly the same way in the following sense. Okay, so the way that I've numbered this on the tape is there's some smear, and then the dots get progressively further and further apart as the acceleration occurs. And then I label the dot 0, 1, 2, 3, and so on, out to dot 9. And then I construct the following data table as we normally do in these types of spark timer labs. Okay, 4 columns. So we're going to have here dot number in terms of n, 0, 1, 2, 3, and so on, up to dot 9. Position of the nth dot, you can make the measurements in terms of centimeters, that's fine. So dot 0 is our origin, and then you measure from 0 to 1, 0 to 2, and so on as always. Okay, time at the nth dot in terms of seconds, 0, 1/60th, 2/60th, etc. Okay, velocity at the nth dot in terms of centimeters per second. Recall the following formula that we can use in situations involving constant acceleration. The velocity at the nth dot is the position of the dot ahead of it minus the position of the dot behind divided by 2 delta t. So recall the example that I always show in the course of doing these experiments. For example, if you want to find the velocity at dot 6, you take the position of dot 7, subtract from that the position of dot 5, and then you divide by 2/60ths of a second. Recall the shortcut, however, instead of dividing by 2/60ths of a second, you can take the numerator and instead multiply it by 30. You can't use the formula, however, for dot 0 because we don't have a dot -1, nor can you do this for dot 9 because we don't have a dot 10. We use the formula here to calculate the velocity for dots 1 through 8. Okay, once you have those velocities, then in order to obtain the acceleration, you graph velocity as a function of time t, draw a best fit line through your points, and then calculate the slope. The slope, of course, is the acceleration in terms of centimeters per second squared, but now at this point, go ahead and convert to meters per second squared. So now we have the acceleration in our expression. We, of course, already know what the mass is. It's 0.2 kilograms. The last thing that we need to determine I is the radius of the pulley. I've provided for you in this folder for this experiment 2 photographs. The first photograph depicts the spark tape itself such that you can make the measurements of the positions for dots 1 through 9. And I've also posted a photograph for you of the pulley assembly such that you can determine what the radius is. Make sure that you measure the radius of the pulley, however, in terms of meters. Once you have all of that information, then you just merely calculate the rotational inertia I. Okay, so summarizing that here. Okay, so what we've done here is you've measured the acceleration in terms of meters per second squared. With the other photograph, this will then give you the radius of the pulley. Make sure that you record the radius once again in terms of meters. And at this point, you just calculate I. Okay, when you do, the units of the rotational inertia, by the way, are going to be kilogram meters squared. Remember, it's mass times distance squared. And then what should you obtain such that you know that we've gotten a good value? you should obtain something in the neighborhood of about 10 to the minus 4 kilogram meter squared, like 2 or 3 times 10 to the minus 4 kilogram meter squared is typical for this experiment. The experimental errors, however, are as follows. There is, of course, friction between the spark tape and the spark timer, and there's, of course, friction with the axle, which we did not take into account. So because there is friction with the axle, this then makes the rotational inertia seem larger than it actually is. So then therefore the value that we calculate is probably a little bit bigger than the actual value of the rotational inertia of the pulley because we're not taking into account the friction that occurs at the axle. Give me a brief description of that in the description of the experimental errors.